Welcome, listeners, again to the second part of our discussion on the igneous rocks. And earlier, we have looked into the various types of igneous rocks and the minerals present in it, and how, based on the idea of the experimental petrology postulated by Bowen, and with the help of Bawan reaction series and the range of crystallization of various silicate minerals, be it a ferromagnesium 1 or a non-ferromagnesium 1. Based on that idea, we have seen that what could be the essential mineral components of a specific igneous rock, be it a plutonic one, be it a hypoabyssal one, be it a volcanic one. Now, going into the mode of occurrence, we have looked into igneous rock, various igneous rock, be it in continent, in the means in your ocean basins, or be it within in the mantle. So now we will be looking at the mode of occurrence. Now, the mode of occurrence is mainly related to the exposures of the rock that we can generally find in field or on the earth crust. So, we'll start or we'll discuss mainly about the mode of occurrence of three kinds of rocks: granite, andesite and basalt, because they occur on the surface of the earth. Largely they are exposed on the surface of the earth. So, first, to start with the mode of occurrence of granite, obviously, like we have discussed earlier, that granite are intrusive igneous rocks, and it is primarily composed of quartz, feldspar and mica minerals. Like, we can also take a cue from the order of crystallization chart that we have discussed earlier. So, the mode of there are various mode of occurrences of your granites, be it in a large batholithic form, then you can have stalks, sometimes some dike and sills and plutons as well. But when we are talking about granite, remember that generally it is the means in case of dikes or sills, granites gets intruded as apletic veins, or you can say apletic dikes sometimes as well. So, it is nothing but a kind of a volcanic equivalent or surface equivalent of granite as we know it. So, the mode of occurrence when we are talking about batholiths, these are large scale, you can say, bodies or large hump like bodies which have protruded the ground or protruded the surface of the earth. So, here is a famous example of half dome batholithic structure in the Yosemite National Park in USA. Then also, if I look at, for example, some structures like a laccolithic structure, some stalk like features. Stalk are nothing but they are kind of intrusive extension from a different batholithic structure. But now, due to the period of long period of or million years of denudation processes, now some of the part of the upper surface has been eroded. So, if I erode the upper surface or the upper half of this diagram, then you can say that you can look into the real intrusive batholithic body of a granite. So, likewise, in case of, if I take Indian example, you can see large granite batholithic bodies in different parts of India as well, be it in the Shingbhum Craton, be it in the Dharwar Craton. You can see or be it in your Rajasthan as well, you can see large batholithic bodies of granite that are present on the surface of the earth. Now, if I think about andesite, so andesite, like we discussed, is an intermediate rock between your mafic and felsic. So, granite strictly a felsic rock. Here andesite is more of an intermediate rock, and they are generally found at the different sites of volcanism on the earth's surface. So, if some oceanic lithosphere is getting subducted beneath a continental lithosphere, like we have discussed when we discussed about the idea of plate tectonics. So, eventually what will happen, this relatively cold oceanic lithosphere will start to melt as it is going down into the mantle, and then subsequently this melts will get turned into your molten lava, and they will be extruded on the surface of the earth at nearby volcanic means your zones of volcanic activities. So there also, so if I look at now at the andesite specifically, like I was mentioning, it is an intermediate rock in composition between basalt and dacite, meaning it contains a silica percentage of around 52 to 63%. It is primarily composed of quartz, feldspar, amphiboles and mica. So you can see there is a difference here. You also have amphiboles in your diorite. And obviously it's an exclusive variety of diorite. Diorite is a plutonic variety, it is the volcanic variety of your diorite. So they are found at volcanic arcs like that we get to see at the Andes mountain belt, and from the nature of the volcanic rock extruded at the Andes mountain belt, the name has been derived from the Andes mountain belt as the andesite rock. So the rock that has erupted along the volcanic chain that is present along the Andes mountain belt along the west coast of South America, you can say that the name of the rock andesite has been derived from this name of the mountain belt. You can also get andesite similar to volcanic arc in case of island arc settings. You can also get, for example, continental arc setting where your andesitic magmas can also form in continental arc. For example, the Cascade Range in the western United States. Then you can also get andesite in your continental interiors, where andesites can be found in, means these are intrusions that can form in the, means again the mode of occurrence of these andesites that are present in the continental interiors, they generally are present as your plutons or sometimes dikes. And obviously the most commonly occurring andesites that you will find will be near plate boundaries. Definitely, again, if I look at the Java Sumatra arc, its extension is obviously present as barren island in the Andaman and Nicobar island of India. So there the composition of the lava that is extruding onto the surface of the earth is mainly basalt, but some basaltic andesite composition are also have been reported. Now coming into basalts, which actually constitute the majority, or you can say almost the complete oceanic crust that is present on the earth. So basalts are also extrusive igneous rock which cool down very fast. That's why they are typically fine grained in nature, as well as they are rich in minerals like plagioclase, feldspar, pyroxene and olivine. Again, if I look at the previous discussion on igneous rock, when we discussed about the order of crystallization, there we have seen that if I am looking at the volcanic equivalent of peridotite, that is obviously your basalt. So your peridotite that is present in the mantle will have a similar composition of that of the volcanic equivalent, that is basalt, which is present on the crust. So there also, if you can remember, the main components according to the order of crystallization of minerals were augite and olivine, and some obviously some feldspar, specifically calcium rich, that anorthite one was present in your both in peridotite as well as in basalt. So your basalt might occur as your volcanic basalts like columnar structures. They exhibit columnar structures like this. There can be occurrence of some pillow basalts if there is some you can say the basaltic magma is rich in sodium and it is getting extruded underwater. So in that case it will form pillow like structures. Then you also have, which is the most dominant mode of occurrence of basalts on the earth, the continental crust part is in form of basaltic dikes and sills. Then also the most fascinating example that we can see in India as well, the presence of Deccan trap, which is a beautiful example of your continental flood basalt. So if you go to areas like Maharashtra, some parts of Gujarat, some parts of Karnataka, it is full of some parts of, means the western part of Madhya Pradesh as well. You will get to see this kind of plateaus, these basaltic plateaus, which are the evidences of large scale continental basalt outpour at some point of time, at specifically at around 65 million years time. So, and the fifth kind of mode of occurrence of basalt is your basaltic cones and cinder cones. So, you can have this cone kind of structure that you can also find in the continental regions, which are referred to as basaltic cones or cinder cones. So, these are the means out of many in kind of or out of many mode of occurrences, these are the common mode of occurrences of your granite, andesite and basalts. Like again going back to this diagram, you can have this idea that based on the components of whether it is containing felsic mineral, intermediate mineral, mafic minerals or ultramafic minerals like that of olivine, again it is grouped into means igneous rocks are grouped into plutonic or intrusive and extrusive rocks broadly. So, you have granite as your plutonic, you have rhyolite as your volcanic equivalent of granite. Similarly, andesite is the volcanic equivalent of the plutonic diorite, basalt is the volcanic equivalent of plutonic gabbro, and komatiite is the, you can say, the means volcanic equivalent of your peridotite. So, obviously from peridotite also the melting of peridotite will also give you basaltic composition and sometimes also komatiite composition. And now if I look at the textures, various texture of igneous rock, I can group it under the various categories. The first one, the first kind of textures are grouped on the basis of degree of crystallization. So, obviously the degree of crystallization means how fast your crystallization is going on. So, if I am looking at a granite, you have a slow, the rate of crystallization of the granitic magma is always slow. On the other hand, if I look at the obsidian, that is obviously silica rich, but in case of obsidian the cooling rate is extremely fast. So, that is why being a silica which should result into formation of well developed quartz grains, it is not forming any quartz grain, it is giving you a, you can say, a smooth surface without the development of any grains that you can recognize in your naked eye. And the intermediate one, you can say there are examples like trachyte, which has the intermediate or moderate rate of crystallization. Based on granularity also, it means that if you can see the grains in a rock, then you can group it under phanetic or phaneritic texture. If you can't recognize or it is so fine grain, then individual grains you can't recognize with your naked eye, it will be considered under aphanetic texture. So, it is just based on the presence of grains, whether there are a presence of grains, you can recognize the grains on the base simply by looking at it, or you can't at all, because it is so fine grain you will not be able to see any grains that has developed in it. Not sometimes it is not even possible to recognize grains even under the microscope, means an optical microscope. Based on the fabric of the crystal also, it now depends that how your individual grains look. So, if I look at a quartz grain like this surrounded by some carbonates here, means calcite grains around the quartz, you can see a very well developed euhedral crystal that is present here. Similarly, if I look at the individual grain shape, for this one I can say there is a pyroxene grain which is giving you a subhedral kind of a structure, and when your grains, individual grains are angular in nature, they do not have a very specific geometry, in that case they are treated as anhedral. Some plagioclase grains you can see here as well, which are anhedral because the grain is going here, going down here, there is no particular geometry of that particular plagioclase grain. So, I will group that under anhedral crystals, talking about individual mineral grains. Now, based on the mutual relationship between the grains, now you have a 2 or 3 or more grains which are related to one another, or the grain boundaries of these mineral grains, they are connected. So, now again based on that also I can group into under 3 categories: idiomorphic, hipidiomorphic and allotriomorphic. So, your idiomorphic will be when your most of the grains that are in connection to one another, they are euhedral in nature. Similarly, for hipidiomorphic, I can say if the grain boundaries or the minerals that are having a shared grain boundary, but the individual mineral is having subhedral shape, then I can consider it under hypidiomorphic texture, and also allotriomorphic one when the mineral grains which are sharing some similar grain boundary, they are all anhedral in nature. So, I can also group it under allotriomorphic texture. But remember always these are done because of some purpose. This nomenclature is not like that we just need to separate 2 or 3 or 4 types of rocks. That is why we are separating it. It has a purpose. The main purpose is actually to look at the history of crystallization or solidification of a rock. So based on that, so based on the textures, be it a single grain, the structure of a single grain, be it the mutual relationship, which is also the definition of texture as a term, that it shows the interrelationship or the mutual relationship between different mineral grains. So, if you are having a set of minerals and they are having some shared boundary between them, so based on the idea of the contact or based on the observation of the grain boundaries between the mineral grains, you can also have an idea that how that rock might have formed. Continuing with this, based on the again mutual relationship of the grains, there are a few more textures like which are grouped under inequigranular texture. The earlier one, idiomorphic, hypidiomorphic or allotriomorphic, those are the types of equigranular texture. In case of equigranular, now equigranular and inequigranular texture, they are broadly differentiated based on the average grain size of individual minerals. So, if in a thin section you are looking a rock that more or less the grain size of all the grains are similar, then you will group it under equigranular. But if you are looking at a thin section where the mineral grains are of different size, or you can say there are 2 or 3 subclasses of your sizes, that one is a large grain, the ground mass that on which the large grains are floating, they are extremely fine grain, but there are a few grains of intermediate size as well. Then definitely there is a size difference between individual grains in that particular thin section. Then we can group it under inequigranular texture. So, again there are a few types of granular texture. The first one is the porphyritic texture, where you have distinctly 2 separate size classes. Your large grains, which are referred to as phenocryst, will float on very fine grain, which is referred to as matrix. So, your very fine grain matrix will make up the ground mass, on which your large scale crystals, which are referred to as phenocryst in case of igneous rock, they will float on that matrix. Apart from that, you have poikilotic texture, where also you have 2 classes of grain sizes of different minerals. Here I can say that small laths of feldspar, or you can say small grains of plagioclase feldspar, they are kind of trapped within a large grain of a pyroxene. So, that way you can also consider that if smaller grains of a mineral, they are trapped or they are present in a large crystal, then they are referred to as poikilotic texture. Then you can also have ophitic texture when there is partial or complete, based on that it is known as ophitic or subophitic. There is partial or complete inclusion of a plagioclase grain within a pyroxene that is larger in size, a pyroxene grain. So, if your plagioclase is partially embedded in that pyroxene grain, then it is subophitic. If it is fully embedded within the pyroxene grain, then it is ophitic in nature. Then you also have intergranular texture, again based on the mainly 2 classes of grain size, you can say, where your plagioclase laths or plagioclase grains, they are forming some triangular or subtriangular structures like this. If I simply take this pen and if I draw, then I can say there are some this kind of features, which you can say there are triangles formed by this laths or plagioclase, and inside them there are either fine grain minerals or there is glass that is trapped. Based on that, it is also differentiated as intergranular. If some more mineral grains are present within this spaces that are formed by some a few plagioclase layers that you can see. If it is filled up with different mineral grains, it is intergranular. If it is filled up with glass, it is intershuttle. So there are these two kinds of intergranular texture, you can say. Then you also have directive texture. Why directive? As the name suggests, it will give you some direction about the rock. Means that when the rock solidified, and it is mostly present in case of volcanic rocks, when your lava is flowing on the surface of the earth, and with in the direction of the flow, it moves away from the, you can say, from higher temperature to lower temperature, or it is cooling down during its flow from one place to another place. It gets solidified with time in its course of journey from one part to another part. Obviously it is molten lava, so it can flow to some distance, depending again on its fluidity and viscosity, that how far your lava can move. So based on this, your grains that are getting solidified in that particular as a result of cooling down or crystallization of the volcanic lava, they get oriented in the direction of the flow. So based on that, there are two types of texture. Again, one is trachytic. There will be also some large, you can say, phenocrysts that are still possible to be present in that, which might have formed at relatively earlier stage, and now when the finally it is crystallizing with a flow in the magma is still flowing, then the rest of the, for example, plagioclase layers will be first of all fine grained, relatively fine grained as compared to, you can say, a plutonic rock. They will be fine grained, but individual crystals or individual layers of plagioclase feldspar, they will get aligned along the movement direction of the molten lava. Similarly, you have also hyalophylitic texture. In this case also there are no evidence or no presence of any large scale phenocryst. It is solely fine grained crystals that are flowing in a particular direction. That is why they are also defining a direction of the flowage of the magma. Plus sometimes they are also dominated with glass, because if it is crystallizing at a very fast rate during its flow, then most of the mineral will not get time enough to get crystallized into its characteristic shape. In that case, it will be a combination of smaller grains as well as some glass in it. So it will define your hyalophylitic texture. Now looking into some other texture like that we also get in plutonic rocks, for example intergrowth textures like graphic and mimictic texture. These are intergrowth of one mineral within another mineral. For example, if I look at this beautiful worm like structure that is referred to as your mimicite texture, there you can see these small blobs or small, you can say, worm like structure of quartz that are present within a large grain of feldspar. So this will be the intergrowth of quartz within your feldspar. So that's your mimicite texture. Some other textures also include like zoning in plagioclase, because plagioclase, if you remember, according to the order of crystallization as well as according to Baynes reaction series, plagioclase is a mineral that belongs to the continuous series of the Baynes reaction series, on the right hand side of the Baynes reaction series. So you have a solute solution between your calcium rich plagioclase, that is your anorthite, and you have a sodium rich plagioclase, that is your albite. So between that you can have continuous solute solution, continuous substitution of one another, and you can also have some other feldspar, for example oligoclase, andesine, labradorite and biotinite, if I grow from albite to anorthite. So you have a total set of 6 minerals or 6 varieties of plagioclase minerals that might be present in a that might result into this due to the substitution between your sodium and calcium continuously. These minerals might also occur as a part or the members of the solute solution between your albite and anorthite. So in case of zoning, what happens, that there is some difference between this specific composition of this outer ring with respect to the inner one, then the outer one, again inner one. So you have alternate rings here like this, and they are referred to as a zoning in plagioclase. There are also 4 to 5 types of zonings that are possible in plagioclase. Maybe we will discuss that sometime else, because that is beyond the scope of the fundamental idea, but possibly we will try to discuss in the later part sometime, when we discussed about igneous phase diagrams and the background reason of or the background, you can say, explanation for the initiation or formation of any kind of texture in igneous rock, but that is for some other lecture. So here we can see this beautiful zoning in plagioclase due to this continuous substitution within the continuous series of plagioclase. So you can have alternate layer of albite and anorthite within a plagioclase feldspar, and that can be recognized with the help of an optical microscope. There is some other which is also important texture, that is a class of reaction texture. There are again a few kinds of reaction texture, but the most common one is a corona reaction texture. So if you are crystallizing a magma that is having some composition of olivine, augite and hornblende, means it has some composition belonging to the olivine group, amphibole group and pyroxene group, then it is possible that there will be some reaction between the olivine and augite, and there will be reaction between augite and hornblende. So as a whole, they might form this kind of corona structure, where your internal part of this grain or the central part of this grain is occupied by olivine, surrounded by augite, and then further surrounded by hornblende. Again, this requires basic understanding of means your some of the igneous phase diagrams, through which we can explain this kind of formation of this kind of textures. Then you also have the classification of igneous rock, where we can classify igneous rock based on its felsic, intermediate mafic and ultramafic nature, based on the percentage of silica. Then igneous rock can be also classified based on the silica saturation, silica saturated, silica undersaturated, silica oversaturated, based on the percentage of quartz in it, and also feldspathoids. And based on the alumina saturation as well, it can be grouped as peraluminous, metaaluminous, subaluminous and peralkaline igneous rocks. So these are the distinctive minerals that are present in this kind of classification. But the most accepted one is your IUGS classification of your phaneritic igneous rock, where you can look at the grains. Phaneritic rocks we have discussed, where you will be able to recognize the grains in a rock. So based on the mineralogical content or the modal percentage, that what is the volume percentage of a particular mineral in a rock, based on that your IUGS classification, the left one is for plutonic rock, the right one is nothing but an equivalent, but of your meant for your volcanic rock. And mainly they are as we are referring to volcanic rock, that means this IUGS classification is mainly considering the aphanitic rock, where you cannot recognize the individual crystals. So so based on that, you can see this means QAP quadrilateral diagram. Here you can see the presence of your granite, here you can see presence of quartz rich granitoid, then syenite, monzonite, monzodiorite. These are the various plutonic igneous rocks. And also on the lower part, where you have void bearing minerals or feldspathoids, there you can also get some rocks like monzocyanite, monzodiorite, which are void bearing. Some cyanide, void bearing cyanide, void bearing gabbro as well. Similarly, if I look at the volcanic equivalent here, then I can see that rhyolite here is taking up the place where you have granite and alkali feldspar granite. So again, I can say that rhyolite is the volcanic equivalent of the granitic composition, and for here you have the, for granodiorite and tonalite region, you have the volcanic equivalent, that is dacite. Similarly, for your quartz cyanide, cyanide region, you have this trachyte. For monzonite, you have latite. Then in the quartz monzodiorite or diorite part, you have andesite. So these are the different volcanic equivalent. You also have the basalt, phonolite and tephrite in this diagram. of your IGS classification. Specifically, this is also an IGS classification of specifically ultramafic rock, because here we are considering solely the mafic minerals, olivine, pyroxene and hornblende. So based on that, they are also segregated as duwnite, peridotite, pyroxenites and hornblendites. Then obviously the most important one for volcanic rock, because it is aphanetic in nature, so you can't always, or it is not easily always possible to determine the minerals present in that, and it is so fine grained that you can't also calculate the volume percentage of those fine grained minerals. So that's why, apart from the IGS classification of volcanic rock, which is similar to that of the well established IUGS classification of plutonic rock, what we have is total alkali silica or TAS diagram, meant mainly for volcanic rocks, where we will take the total percentage of silica on one side, on another side you have the total percentage of Na2O and K2O, which will reflect the presence of ultra basic, basic, intermediate and acidic but volcanic rock. We are no longer into felsic or felsic rock, we are now or we are no longer into your plutonic rock, we are strictly within your volcanic rock. So there again this diagram shows where your individual rocks, be it your rhyolite, which will have a very high silica content like that of granite, will be placed here. Similarly, basalt, which is having a relatively much lesser content of silica in it, will be present here, which is again an equivalent of your gabbro. And also there are other rocks like here andesite you can see, then you can see your tephrite, basanite. So these are all your ultra basic or basic igneous rocks. So this is the only way, which is obviously derived chemically based on the chemical percentage or weight percentage of silica and the complete or total waste percentage of Na2O plus K2O. So that will give you this diagram of TAS diagram. So here I would like to conclude the preliminary discussion on igneous rock. So thank you.